Section 13.4, calculating the pH of strong acid solutions. So when we're solving acid-base problems like this, there's a couple of things that we want to consider. These are all what we are going to term neutralization reactions, in which an acid and a base are going to react with each other. But what you want to do is think chemistry. Focus on the solution components and their reactions. You want to be systematic. Acid-base problems are going to require a step-by-step approach, and be flexible. Treat each problem as a separate entity. Don't try to force a given problem into matching any of the problem patterns you've solved before, and look for both the similarities and the differences between different classes of problems. Be patient. Pick the problem apart and do it in its workable steps, and be confident. Look within the problem for the solution and let the problem guide you. Understand and think. Don't just memorize. This is not something where you can sit down and say, oh, here's the same pattern each time. I'm going to get this answer. Right? We're going to do a lot of stuff where we look at things like a limiting reactant problem. And as you should remember from Gen Chem, you can't just take a limiting reactant problem, kind of visualize the answer and be right. You've got to go through the individual steps. Right? So the steps involved in calculating the pH of a strong acid solution is you're going to determine the major species in solution. So that means, what have I put in there? Did I add HCl? Did I add sodium hydroxide? Did I add a second strong acid or a strong base? Determine the dominant reaction that will take place. So determine which components are significant and which can be ignored. And we're going to focus on the major species, the solution components that are present in relatively large amounts. So, for example, we're going to see a little bit later on where we've got polyprotic acids that can generate more than one hydrogen in solution, potentially, that really it's only going to be successive deprotonations that will matter. The contribution of secondary ionization will be minimal. Determine if the reaction is an equilibrium reaction or a reaction that will go essentially to completion. Strong acids, strong bases. React all the major species until there is an equilibrium reaction. And then if they ask for it, solve for pH. And that's oftentimes what they're going to look for. Why? Because if you're grading something, looking at something going, oh, the pH is 2.3, it's a lot easier to see, like, boom, you've got that right answer. All right. So let's do a quick concept check. Consider an aqueous solution of 2 times 10 to the minus 3 molar HCl. What are the major species in solution? So it's asking you, what does this dissociate into? Right? I've got 3 major species, H+, Cl-, and H2O. What is the pH going to be? Well, our pH is just minus the base 10 log of H+ concentration. Because HCl is a strong acid, it will completely dissociate. So if I've got 2 times 10 to the minus 3rd molar HCl, I'll have 2 times 10 to the minus 3rd molar H+. So minus the base 10 log of that is going to be 2.70. Now let's look at the pH of a 1.5 times 10 to the minus 11 molar solution of HCl. Well, if I go through and I do that math, the pH is going to be minus log of 1 times 10 to the minus 11, which is going to be 10.82, right? Is it right? Well, that's the pH range of a base, and you shouldn't have an acid in that base range. This answer neglects that the water is a major species, and it turns out to be the major contributor of H+. So if our HCl is only giving us 1 times 10 to the minus 11 molar, and our other species, so here's our HCl protons, 0.0000000007, HCl protons versus 0.000007, right? It's several orders of magnitude more protons coming from the water than from the acid. And that H+ is primarily coming from that auto-dissociation of water. So our major species, remember, were H+, Cl-, and H2O. And here that H2O is giving us just more H3O+, than we would get from our acid. So water is the major contributor, so our pH is 7. So just a good rule of thumb. If you've got an acid concentration that's times 10 to the minus 7, you're running up against Kw, you probably just stick with Kw. Right? So let's calculate the pH of a 1.5 times 10 to the minus 2 molar of solution of nitric acid. Our major species are going to be H+, nitrate, and water. The reaction controlling the pH is going to be H2O plus H2O, giving us H3O plus and OH minus. And that's because it's the only equilibrium reaction. NO3 minus is not going to be a base in water. However, the major source of H plus is from the nitric acid, so we're going to say our pH is going to be minus the base 10 log of 1.5 times 10 to the minus 2, or 1.82. All right, cool. I want you to pause and think for a second about what we're doing, because we're going to undergo a major shift in topic. Now we're going